All right, let's jump right into this explainer and look at how we actually teach an AI to handle its biggest mistakes. When we talk about machine learning, we usually spend all our time focusing on the incredible predictions it gets right. But the real secret to a highly accurate model, that actually lies in how it processes the things it gets wildly, terribly wrong.
So set the stage for a second and think about this. How does a machine even know when it's made a mistake? An algorithm doesn't have intuition, right? It doesn't feel a sense of embarrassment when it messes up a prediction. For an algorithm to actually learn from being wrong, it needs a highly specific mathematical set of instructions that quantifies exactly how incorrect it was.
Here's a quick roadmap of where we're headed in this explainer. First, how machine learning learns. 2, meet MAE and MSE. 3, the outlier effect. 4, our sensitivity showdown. And finally, number 5, making the right choice.
Okay, Section 1. How machine learning learns. Everything basically centers around this concept right here, the loss function. Think of the loss function as, well, a mathematical ruler. It literally measures the physical distance between what your model predicted and the actual ground truth value. Now, what's absolutely crucial to understand is that loss focuses purely on the distance of the error, not the direction. If a model predicts a value of 2, but the real value is 5, the calculation doesn't care that the result is -3. Actually, scratch that, it just completely removes the sign and only cares that the distance is exactly 3 units away.
During the training process, the algorithm's ultimate goal is to minimize this loss. It wants to bring that mathematical distance down to its lowest possible value. So generally speaking, the lower the loss, the better the model's predictions. But a quick word of caution here. A loss equal to exactly 0 isn't really a victory. In fact, it usually points to a dangerous problem called overfitting, where the model has basically just memorized the training data and is going to fail completely when you show it new, unseen information.
Moving on to Section 2. Meet MAE and MSE.
Let's contrast our two contenders side by side. On the left, we've got MAE, or mean absolute error. MAE calculates the error simply by taking the absolute value. It literally just drops the negative sign. Think of MAE as this very even-keeled judge. It treats every single mistake with the exact same level of severity. On the right, we have MSE, or mean squared error. MSE removes the negative sign by multiplying the error by itself. It squares the difference. So if MAE is the fair judge, MSE is the strict disciplinarian of our models.
Now check out how the mathematical difference of squaring completely changes the penalty size. MAE, which is also known as L1 loss, creates a linear penalty. If the error is 5, the penalty is based on 5. Pretty straightforward. But MSE, known as L2 loss, creates an exponential penalty. Because it squares that difference, an error of 5 suddenly explodes into a penalty of 25.
So to summarize their fundamental relationship, both of these functions solve the negative number problem so that errors don't cancel each other out, right? And both of them calculate the average error across your entire data set. But that one single mathematical step, squaring the error in MSE, is an absolute game changer for how the machine learns.
Let's look at Section 3, the outlier effect. I want you to imagine a scenario. Your model has been making smooth, highly accurate predictions all day. And then, suddenly, out of nowhere, it is wildly, spectacularly wrong about a single data point. How do our two loss functions handle this massive, unexpected error?
This massive error is almost always caused by an outlier, and an outlier is just a data point that falls way outside typical ranges. For example, let's say your model is predicting fuel efficiency based on car weight. Most 3,000-pound cars might get around, say, 20 miles per gallon. If a 3,000-pound car suddenly shows up in your data getting 40 miles per gallon, well, unless it's coasting down a giant mountain, that is a massive outlier. To your model, it's a shocking anomaly.
Which brings us to Section 4, the sensitivity showdown.
Let's look at the actual math to see how they handle that anomaly. With a standard error of 2 units, MAE penalizes the model by 2 and MSE penalizes it by 4. A noticeable difference, but totally manageable. But look at the outlier. An error of 10 units results in an MAE penalty of 10, but the MSE penalty, it literally explodes to 100.
This is a really fascinating functional quirk of squaring numbers. If you square a number smaller than 1, say 0.9, it actually shrinks down to 0.81. So MSE is actually kind of forgiving of tiny fractional mistakes.
But the very second an error is greater than 1, MSE completely loses its mind and explodes the error into a massive penalty. It literally forces the algorithm to pay extreme attention to the largest mistakes.
As the source material plainly states, MSE moves the model more toward the outliers while MAE doesn't. Because the penalty of 100 in our previous example is just so astronomically high, the training algorithm kind of panics. It desperately wants to reduce that specific 100-point penalty, so it drags the entire model's prediction line toward the anomaly just to ease the mathematical pain.
If we visually map this out on a graph, the regression line for MAE basically ignores the noise. It stays farther from the outlier and stays nice and tight to the vast majority of your normal data points. The MSE line, on the other hand, is physically pulled away from the main cluster of data, trying to accommodate that one weird anomaly just to shrink that squared penalty down.
So the crucial point here is this. Your choice of loss function directly dictates how sensitive your AI is going to be to abnormal data. MAE's lack of sensitivity makes it highly robust to outliers. MSE's extreme sensitivity, though, means outliers will skew your entire system significantly. Let's wrap it up with Section 5, making the right choice.
Let's start with May. You should choose May when outliers are just random noise that your model should mostly ignore. A perfect example is a food delivery app. If a delivery usually takes 20 minutes, but one driver gets stuck in a total freak once-in-a-year traffic jam and takes 2 hours, you really don't want your algorithm thinking 2 hours is the new normal. May prevents that rare anomaly from skewing the delivery estimates for everyone else.
Conversely, you're going to want to choose MSE when a large error is incredibly dangerous or costly. Consider a real estate pricing model. If your model is off by just 5% on a $200,000 house, that's a $10,000 real-world financial miscalculation. In this scenario, large errors are entirely unacceptable. You want MSE working as that strict disciplinarian, heavily penalizing those massive financial deviations so the model works tirelessly to fix them.
So, here is your final decision framework. Use MAE to ignore wild outliers and get an average error in the exact same units as your data. Use MSE to ruthlessly penalize dangerous, costly errors. And for the advanced learners out there, if you find yourself in a scenario where you need a bit of both, like robustness to extreme outliers but sensitivity to moderate errors, look into a hybrid function called Huber-Loss. It kind of combines the best of both worlds.
Ultimately, the big takeaway here is that math isn't just a jumble of numbers. The formula you choose is a literal set of instructions defining your model's teaching philosophy. It tells the machine exactly what it should care about and exactly what it's allowed to ignore.
I'll leave you to consider this final thought about your own data. If your model's biggest mistakes cost you the most, is your current loss function hiding them, or is it highlighting them? Make sure you're using the right mathematical ruler for the job. Thanks for joining me on this explainer, and keep learning.